Bismillahirrahmanirrahim. My name is Arit Fatma from BS Chemistry. Today my topic of presentation is stereochemistry. First we talk about the definition. Stereochemistry is the branch of chemistry that involves the study of different arrangements of atoms in molecules. The first content is enantiomers and tetrahedral carbons. The question arises, what causes molecular handedness? To see how molecular handedness arises, look at generalized molecule of top type CH3X, CH2XY, and CHXYZ. On the left are three molecules, and on the right are their images reflected in a mirror. The CH3X and CH2XY molecules are identical to their mirror image and thus are not handed. If you make a molecular model of each molecule and its mirror image, you will find that you can superimpose one on the other. The CHXYZ molecule is not identical to its mirror image. You can't superimpose a model of molecule on middle model of its mirror image for same reason that you cannot superimpose a left hand on right hand. First diagram is CH3X structure, tetrahedral, and they are CH3X and CH2XY are the mirror image of each other, and CHXYZ are not identical and are not same. It cannot superimpose on each other. Then we talk about enantiomers. What are enantiomers? Molecules that are not identical to their mirror image is called enantiomers. The word enantio is a Greek word which means opposite. Enantiomers are related to each other as a right hand is related to left hand. Whenever a tetrahedral carbon is bonded to four different substituents, for example, lactic acid 2-hydroxypropanoic acid exists as a pair of enantiomer because there are four different groups: hydrogen, hydroxyl and CH methyl, and CO2H. These are the four groups which is bonded to central carbon atom. Both are found in sour milk, but only the enantiomer occurs in muscle tissues. This is the structure of lactic acid, a molecule of general formula CHXYZ. This molecule is not superimposed on each other and they are not identical. Then lactic acid positive and lactic acid negative. No matter how hard you try, you can't superimpose a molecule of lactic acid on a molecule of negative lactic acid. If any two groups match up, say hydrogen and CO2H, remaining two groups doesn't match. This is the structure in which hydrogen and CO2H can match, but the other two groups are not matched on each other. The reason for handedness in molecules means chirality. A molecule that is not identical to its mirror image is called chiral molecule. Chiral is a Greek word which means hand. How you can predict whether a given molecule is not chiral or is chiral? By far the most common in an organic molecule is the presence of carbon atom bound into four different groups. Chiral carbon is attached with four different functional groups. Detecting chirality centers in a complex molecule takes because it's not always apparent that four different groups are bonded to given carbon. The differences doesn't necessarily appear right next to chirality center. For example, 5-bromodecane is a chiral molecule because it is attached with four different groups. A butyl substituent is very similar to a pentyl substituent because it is not identical. This is the structure of 5-bromodecane, which is chiral molecule because it is attached with four different functional groups. And the other examples are carbon and notketone. Carbon is a spearmint oil and notketone grapefruit oil. Another way to identify chiral molecule is to look for presence of plane of symmetry. Then we talk about symmetry plane. What is symmetry plane? A symmetry plane is one that cuts through middle of molecule in such a way that one half of molecule or object is mirror image of other half. For example, this is the structure propanoic acid and lactic acid. This symmetry plane is that when we cut the center of the molecule, then the first half is the mirror image of other half. For example, propanoic acid and lactic acid. And lactic acid is not a symmetry plane uh, in this present because they are not the mirror image, because in this one half is not the mirror image of other. Then we talk about the optical activity. The study of chirality originated in early 19th century during investigations by French physicist Jean Baptiste Biot into nature of plane polarized light. A beam of ordinary light consists of electromagnetic waves that oscillate in an infinite number of planes at right angles to direction of light travel. When a beam of ordinary light is passed through a device called a polarizer, only the light waves oscillating in single plane pass through and the light is said to be plane polarized. When light is passed through a single plane, then it is called plane polarized. Light waves in all other planes are blocked out. Not all organic substances exhibit this property, but those that do are said to be optical active. Those compounds which are capable of passing the light in a single plane are called optical active compounds. The angle of rotation can be measured with an instrument called polarimeter. Uh, the light then moves to a solution of optically active organic molecules is placed in a simple tube. Plane polarized light is passed through tube and rotation of polarization plane occurs. The light then goes through a second polarizer called the analyzer. By rotating the analyzer until the light process through it, we can find the new plane of polarization and can tell to what extent rotation has occurred. This is the diagram of polarimeter. We have first is observer, then analyzer, then sample tube containing organic molecules, and polarizer, then light source. The material is placed in a sample, which is the plane polarized light is passed through the analyzer, and we can observe the rotation. In addition to determine the extent of rotation, we can also find the direction. When optically active molecules with polarized light left of the polarizer, then it is called levorotatory, and when other rotate polarized light to the right are called the dextrorotatory. By convention, rotation to the left is given a minus sign and rotation to right is given a plus sign. For example, morphine is a levorotatory and sucrose is dextrorotatory. The extent of rotation observed in polarimetry experiment depends on number of optical active molecules encountered by light beam. It depends on sample concentration and sample path length. Then what is specific rotation? The specific rotation of compound is defined as observed rotation when light of 589.6 nanometers wavelength is used with a sample path length of 1 decimeter. This is the formula of specific rotation, which is observed rotation by path length multiply concentration. When optical rotation data are expressed in standard way, the specific rotation is the physical constant characteristic of a given optically active compound. For example, minus lactic acid has specific rotation of 3.82 but in opposite direction and plus lactic acid has 3.82. The two enantiomers rotate plane polarized to same extent but in opposite direction. This is the table for the specific rotation of some organic molecules. Penicillin has 233, sucrose plus 66.47, camphor 44.26, and chloroform has zero specific rotation. Cholesterol contains minus 31.5, morphine minus 132, cocaine minus 16, and acetic acid has no specific rotation, which is zero. Then we talk about Pasteur's discovery of enantiomers. Although the structural theory of Kekulé had not yet been proposed, Pasteur explained his results by speaking of molecules themselves, saying, "There is no doubt that it is no, there is no doubt that there exists as asymmetric arrangement having a non-superimposable image. It is no less certain that the atoms of levo acid possess precisely the inverse symmetric arrangement." Pasteur's vision was extraordinary, for it was not until 25 years later that his theories regarding the asymmetry of chiral molecules which were confirmed. Today we would describe Pasteur's work by saying he had discovered enantiomers. Enantiomers are called the optical isomers, which is enantiomers are those superimposed on each other and have identical properties such as point and boiling point. Enantiomers are different in direction in which they rotate plane polarized light. Then the next step is sequence rules for specifying configuration. For specify the method used employs the same sequence rules for specifying A and Z alkene stereochemistry. Let's briefly review these sequence rules. The first rule is look at the four atoms directly attached to chirality center. For example, chiral carbon, which is attached with four different functional groups, and rank them according to atomic number. The atom with highest atomic number has highest ranking, and the atom with lowest atomic number has lowest ranking. The second rule is if a decision cannot be reached by ranking the first atom in substituent, look at second, third, or fourth atom away from chirality center until the first difference is found. And the third rule is multiple bonded atoms are equivalent to same number of single bonded atoms. Having ranked the four groups attached to chirality center, we describe the stereochemical configuration around the carbon by orienting the molecule so that the group with the lowest ranking points directly back away from us. If a curved arrow drawn from the highest to second highest to third highest ranked substituent is clockwise, we say that the chirality center has R configuration. If an arrow from one end to second and third is counterclockwise, the chirality center has S configuration. In this is the example in structure shows the uh, clockwise rotation is R configuration and anti-clockwise rotation is S configuration. These are some more examples of minus lactic acid is R configuration because it moves in negative left side. In R configuration, the rotation is on the right side and in S configuration is on the left side. Other examples are provided, which is S glyceraldehyde 2,3 dihydroxypropanol, and its specific rotation is minus 8.7. And the next is S-alanine, 2, and its specific rotation is plus 8.5. Then the next topic is diastereomers. Molecules like lactic acid and glyceraldehyde are relatively simple to deal with because each has only one chirality center and only two stereoisomers. Take the amino acid threonine, 2-amino-3-hydroxybutanoic acid for because threonine has two chirality centers, C2 and C3. There are 22 for 2 to 4 possible stereoisomers. This is the example 2R3R and 2S3S. These two molecules are the mirror image of each other, and these two molecules are not superimposed each other, and 2R3S and 2S3R are the enantiomers of each other. The four stereoisomers of 2-amino-3-hydroxybutanoic acid can be grouped into two pairs of enantiomers. 2S3S is the mirror image of 2R3R, and 2S3S stereoisomer is the mirror image of 2R3S. For example, in this diagram, we can show that 2R3R and 2S3S are the mirror image of each other, and 2R3S are the mirror image of 2S3R. Diastereomers are stereoisomers that are not mirror images. We use the right hand left hand analogy to describe the relationship between two enantiomers. The diastereomers are similar, but they are not identical and they are not mirror images. The difference between enantiomers and diastereomers. Enantiomers have opposite configuration at all chirality center, while diastereomers have opposite configuration at some chirality center but the same configuration at others. Of the four, only 2s3r isomer occurs naturally in plants and animals and is an essential human nutrient. The result is typical. Most biological molecules are chiral, and often only one stereoisomer is found in nature. This is the table for the relationship among the four stereoisomers of threonine. First column is stereoisomers, then middle column is enantiomers, and the third is diastereomers. These molecules are the first column in this 2 or 3 are the stereoisomers of each other, and 2s3s are the enantiomers, and 2r3s and 2s3r are the diastereoisomers. Then we talk about meso compounds. Look, let's look at one more example of compound with two chirality centers, the tartaric acid. Used by Pasteur, the four stereoisomers can be drawn as follows. The tartaric acid is the have two chirality centers, and in this molecule compound, the four stereoisomers can be drawn. The 2R and 3R and 2s3s are the mirror image of each other, and the other is 2r3s or 2s3r are the mirror image of each other. The mirror image 2r3r and 2s3s structures are not identical and therefore represent an enantiomeric pair. But the other 2r3s and 2s3r are identical and have the rotation of 180 degrees. These are the stereoisomers 2r3s and 2s3r. They can rotate on 180 degrees Celsius and they are the identical of each other. The 2r3s and 2s3r structures are identical because the molecule has a plane of symmetry which is called a chiral molecule. The symmetry plane cuts to C2C3 bond, making one half of molecules a mirror image of other half. Because the plane of symmetry, the tartaric acid stereoisomer is achiral and it has two chirality centers. Such compounds that are achiral yet contain chirality center are called mesocompounds. For example, tartaric acid. Tartaric acid contains two chirality centers, but it is also achiral molecule. So that tartaric acid is called mesocompound. Some physical properties of uh, three stereoisomers of tartaric acid is and enantiomers have identical melting points, solubilities, and densities, but differ in sign of their rotation of plane polarized light. The mesoisomer is diastereomeric with positive and negative forms. It is therefore a different compound altogether and has different physical properties. And this is the table for some properties of stereoisomers of tartaric acid. Stereoisomers plus minus and meso, melting point, specific rotation, density, and solubility at 20 degrees Celsius, gram per 100 ml H2O. Serum isomer in positive form, its melting point is 168 to 170, and its specific rotation is plus 12, and its density is 1.7598, and its solubility is at 20 degrees Celsius is 139.0. And in negative form, the melting point is 168 to 70, specific rotation is minus 12, and density is 1.7598, and solubilities are 139.0. But in the case of meso compounds, the melting point mm, is 146 to 148, and its specific rotation of meso compound is 0, and density is 1.6660, and the solubilities of the meso compounds is 125.0.